Good morning. Sorry for the crashes the last 2 days. I think I may have figured them out yesterday. I ran a software thing that checked and repaired anything on the hard drive that had problems, and then I discovered something else on the power supply on your computer. I don't know if anybody's ever opened up the box or not, but there are lots of wires coming off of it, many of which may not be used, and they aren't on this particular computer. However, one of them was very close to, the end of it was really close to the motherboard plane, and if I jostled the computer a little bit, it would end up bouncing that wire against the motherboard plane and shorting out, and that made the thing kind of crash instantly. Although I'm not sure which one of the things might have been the problem, but I've been able to have a couple of Zoom meetings since then. I had one this morning with the people from the software service I'm using in astronomy, and no problem so far. So I have my hopes up that we've solved that. Noah, it looks like you got your computer fixed, or else you're watching this on your phone. And let's see, Lily and Nolan, I heard from you that you'd gotten the electronics packages okay. I just wanted to show you something real quick. I'll get a couple pieces of hardware before we change over to the share screen thing. Well, I'll change over to it first. Who knows, maybe it was opening this that made things crash. I hope not. I'm doing okay. Yep. Okay, let's see. My mouse is still operating, which means my computer has not frozen. This is the multimeter that I mentioned to you, and if you already had one, you wouldn't have ordered this, but these meters tend to come with this particular set of leads, and I'll just plug this thing in here. The common ground on it is here, and just from habit, most people plug the black lead into there, although the leads are sort of independent of everything, and it doesn't really matter which one you plug into what, although it is easier to keep track of if you use different colored leads. So let's suppose that you wanted to be measuring voltage or ohms, or this even has a frequency counter. Then you'd plug the other lead into here. And the thing is, with these leads, all they have at the end of them is a little point. So you can make temporary contact to something with those little points, but if you want to have a permanent connection and then maybe vary something in the circuit with that permanent connection, these don't work. So I ordered some additional leads from Amazon. Oh, this is a temperature sensor that comes with it. Haven't experimented with this yet, but I ordered some leads from Amazon. This is just a pair that are the same color. And these have a banana plug that goes into the same thing, but on the end they've got some alligator clips, and these are pretty well-built alligator clips, at least on the ones I ordered, and they're fairly strong, and you can make a good permanent connection. And when we start doing the circuits, I'd like you to use these things so you can just kind of keep checking things. they're sort of handy. So anyway, that's stuff that's in the package that I mailed to you, and I hope it arrived in good shape. And let's see. So we're still going. I see things changing on my screen, so it hasn't crashed yet. Yeah, I'll just leave that up there. Anyway, Gauss's law is what we're investigating. I've tried to have a couple of introductions to electric flux with not much success so far, but well, maybe I'll talk about that one problem here, wherever I put it. This one. And I think this is probably where we crashed yesterday, as near as I can tell. I don't think you've actually seen this one, have you? Or have you seen about that much of it?
I think we got to maybe part D on it.
Part D? Oh, okay.
But that was just writing out the equations for each one. I don't know
Okay.
if we've gone into much explanation.
Yeah, the idea is, though, that we were using symmetry arguments pretty much for all of these things. And did I do the sphere, the electric flux through a sphere yesterday?
You didn't get to doing the sphere.
I did not?
You didn't set up the integral yet.
Okay. I'll do that for starters today. And we'll just see how that works. So we'll put a little point charge Q here, and that'll be the thing that we're going to have that's going to generate the electric field. And I'll just draw a sphere around it. And this is only a two-dimensional representation of the sphere, but let this thing have a radius r. And I'd like to calculate the flux of the electric field through this sphere. Well, for a point charge like that, hopefully things are still working. My lights just dimmed for a second, and I'm getting paranoid about everything now. The electric field will be radially away from this thing in every direction. And if I just sort of represent it this way, there we have it. And then I'll just fill in a couple of the half ones. Whoops, didn't need that one. Maybe one here, one down here, one down here. But the electric field will have spherical symmetry, which means from any direction, it's going to look the same, radiating outward from that point charge there. And if I pick a little chunk of the sphere here that has an area dA, and that I'm writing as a scalar, but dA as a vector would be something that points out in this direction. This would be a vector with magnitude dA that points in the n hat direction. N hat is just a unit vector perpendicular to the surface of the sphere at that point. And so this would be dA in the n hat direction. Okay, and that n hat, because it's on the surface of a sphere and it's perpendicular to it, it's along a radius from the center of the sphere and in the same direction as that. So, in fact, it's going to be a distance capital R away from the center of the sphere and pointing right out there. Well, that's the same direction the electric field is going to point there. And so the little bit of electric flux that you get through that tiny area, and I'd call that d phi sub E, will equal the electric field dotted with dA, and this is the electric field at that point. And the electric field at that point is going to be K times Q over capital R squared in the n hat direction, dotted with the dA in the n hat direction. So that's the little increment. Now, a unit vector dotted with itself is 1. You get the magnitude of the unit vector, which is 1, times the magnitude of the unit vector, which is 1, times the cosine of the angle between the vector and itself, which is 0. The angle is, the cosine of 0 is 1. So n hat dot n hat is just 1. And so this little d phi sub e here is equal to k q over r squared times dA. Now, the flux through the entire sphere is going to be the integral of this thing, kq over capital R squared times dA, and this much of it is a constant. And so I can pull those outside of the integral, and I'll just get k little q over R squared, and the integral of dA over the surface of that sphere. But that's just going to be the surface area of the sphere, which is, this part stays the same. Surface area of a sphere is 4 pi capital R squared, and this simplifies to that, and that k we're using is actually a shorthand way of writing a different combination of units, which is 1 over 4 pi epsilon naught. And so then I've still got the q. This is just the k. And then I've got a 4 pi here. And that's all. No more epsilon or no more r's. Well, the 4 pi's divide out, and I just get the flux of that electric field is equal to the charge that I have at the center of it divided by epsilon naught. And there isn't any dependence on the radius of the sphere anymore. It divided out. We used a sphere capital R. If we used one twice as big, the electric field would be 1/4 of its value because it gets weaker with the square of the distance right there. But the surface area of the sphere would be 4 times as big because it depends on the square of the distance again, but it's not in the bottom, it's in the top. And so the flux of the electric field through a sphere that is centered on a charge is just q over epsilon naught. Now, Gauss's law takes advantage of that divergence theorem. Okay, it's still working. I'm checking my screen every once in a while. Gauss's law depends on something, the divergence theorem, that shows up in multivariable calculus at the tail end of the course. And with that, you can demonstrate that it doesn't matter where you stick the charge q, the total flux through the sphere will be the same no matter where. And I'll give you an expression of that here in a little bit. But this means that's the flux of the electric field through the sphere. If I go back to my cube idea here, the total flux through the cube is also going to be, it's going to intercept the same field lines that the sphere would, and the net outward flux of the electric field through the cubical surface, C on there, is going to equal q over epsilon naught. Then use symmetry arguments to find the flux of the electric field through each face of the cube. Well, we've got symmetry. The charge is at the center. Every face of the cube will have the same amount of flux through it, but there's 6 faces of the cube, and so the amount through each face is just going to equal Oops, this is flux of the electric field through the entire thing per face. The flux of the electric field is going to be 1/6 of Q over epsilon naught. And then finally, E, which of the answers would change if the charges were not at the center of the cube? Well, then you break the symmetry. However, the total flux through the cube is going to be the same. All it depends on is the amount of charge that's inside of it. That's kind of a Gauss's law argument, so that's not immediately obvious. But through each face, it's going to change if you move the charge around inside there. But still, the total will be the same. And I'm not going to have you worry too much about this. I would sometimes extend this question and ask, what if you put the charge right at this corner instead? What would be the flux through the faces of the cube? Well, what happens in that case is that, or what would be the field lines through each face of the cube? What happens in that case is that you can attach 7 other cubes that would be connected at this point. And so you could attach one that goes right here, looking like this. And then you could attach 2 more on that same level, and then 4 more below it. Well, what that means is the flux or the field lines are going to be divided up into 8, and this particular cube is only going to get 1/8 of those field lines. And so that's something that's different. And this face, and the bottom face won't have any field lines at all because they're radially away from the charge. And so they'll lie in the plane of these 3 faces, and they won't have any of them that are intersecting it. So you can think about that a little bit. I'm not going to spend a whole lot of time on it today. What I'd like to do, though, is go on to another problem. And this is one that will be easy to do with Gauss's law when we actually start approaching it. But it's something that I'll give you an idea of the difficulty of doing this without Gauss's law. And if you want to actually do an integral for that, you can play with it. But consider an imaginary cylinder with a radius of r equals 0.250 meters and a length of that has an infinite line of positive charge running along its axis. So here's the idea here. You've got this line of positive charge, and I'll draw it going at some kind of an angle here. So this thing is infinitely long. Now, in Gauss's law, something we do is that we look at some situations of symmetry, and one of them is for an infinite line of charge, and another one is for an infinite plane of charge. Well, there's no such thing as that. However, if you get close enough to a line of finite length, like say this thing is 3 meters long, if you get, say, 0.5 millimeter away from this, compared to 3 meters, or however many meters you happen to have, it'll look like an infinite line of charge. It's like standing on the surface of the Earth, it looks like a flat plane, but we happen to know that it's a curved surface, part of a sphere. Still, it looks like a flat plane. And so it's that kind of an approximation that works out in real life. Anyway, infinite line of charge, and we just happen to have this imaginary cylinder, which I'll draw with dashed lines. And when we get to Gauss's law, we'll refer to a surface like this as a Gaussian surface. So we'll be doing that. Anyway, then we've got a uniform charge per unit length of lambda, 6.00 microns or micrometers per centimeter. I'll just replace micro with times 10 to the minus 6th coulombs per meter. And what else we got? That's about all we need. What's the electric flux through the cylinder due to this finite line of charge? Okay. Well, to figure that out, I'll need to know what is the electric field a distance r away from this thing. And have to mess around with that and figure it out. So I'll go to a new sheet of paper here for this. Calculate the electric field a distance d away from an infinite line of charge. Okay, so this will be our infinite line of charge. And I'm going to pick my origin to be right here. Oh, I'll cross that out. I'm going to do this at distance d. Oh, I'm going to put the distance d below it. Okay, anyway, here's my origin. This little distance d is where I want to calculate the electric field. And I need to take into account every bit of charge on this infinite length of charged rod. Okay, well, I'll let x point in this direction. And this thing can have a little chunk of charge, can have a length dx. The amount of charge on this, dq, will equal lambda times dx. Remember, lambda is charge per unit length. If I multiply it by a little chunk of length, charge per unit length times length will just give me charge. And so that'll be the charge on this thing. This little thing will generate an electric field that points directly away from that little charge element. Let's see. I'm going to do a little bit of stuff here. That's about in the right direction. Okay, this angle theta is equal to this angle theta. Those are called complementary angles. That's not a very good theta there. That's better. Complementary angles, when you have a straight line and you have, I don't know what the heck's going on. Anyway, they're complementary angles. Oh, parallel lines or something. Yeah, here's a line that's parallel to that one. And those angles are equal. I always call them alternate interior angles, but they're not. It's sort of related to that, but same bit of stuff. Okay, well, this little chunk here is going to be DE, and I'm going to put a arrow on top because it's got a direction to it, a magnitude and a direction. The magnitude of DE is going to be K times the amount of charge that I have here. So K dq over this distance here, which I'm calling little r, and it's the distance from the charge to that point. So I'll just say that's r squared. So that's the magnitude of the electric field. If I actually write it as a vector expression, dE, it will equal that magnitude. And then to get the x component, I would multiply it by the cosine of theta. Okay, if I bring this up, make this a bit bigger here. Here's theta, here is dE. This side here, which is in the x direction, divided by that, which is going to be the hypotenuse, will equal the cosine of theta, adjacent over hypotenuse. So this will equal dE cos theta in the I hat direction. And I didn't pick a direction for y yet, but I'm just going to let y point that way, downward this time. This one will then equal dE sine theta in the j hat direction. So I'd have that in there. Okay, well, that means I'll have the cosine theta in the I hat direction plus the sine theta in the j hat direction. Okay. So I've got two integrals that I'm going to have to do here. And I'm not going to worry about variables at first, but if I calculate the two components separately, e sub y will equal the integral over that entire line of k dq over r squared times the sine of theta. And my limits of integration are going to be from minus infinity to infinity on the this thing here. But let's see, can I do anything to simplify that? Oh, I'll do the e sub x first. Actually, that one's easier to deal with. Have I got my sines and thetas correct there? Let's see, that's dE cosine theta in the I hat direction, sine theta in the j hat direction. I think those are right. Yeah, should be. All right, that'll be the magnitude of e sub x. Now, for e sub x, here's the deal. When you're going from way out there at infinity into here, you'll have stuff, positive charge if lambda is positive, and the net effect will be an electric field that's pointing to the right. When you go from 0 out to infinity, the net effect of the electric field of all those charges will be something pointing to the left. And from symmetry, you've got just as much on the left side as you have on the right side at the same distances. The x component of the electric field should vanish. And so that's something that should come out of the integral. And we can set this thing up to test that idea. For e sub y, we're actually going to have to go some work to figure this out. But let's see what we can do with this side of the expression here. Cosine of theta, okay, that's going to equal the value of x that we have here divided by this r thing. And so let's see, which way do I want to call that positive? I need to keep track of a sign here somehow. Although, let's see, I'm up there. Yeah, I'm not sure how that's going to work. I don't think it matters for this one, but x over r. And so, and dq was lambda dx. And r is equal to the square root of x squared plus little d squared. So if I make all of these substitutions here, instead of having r, dq, and cosine of theta, I would get everything in terms of a single variable, k lambda dx, and then equals integral of minor details let's see, cosine theta was wherever it is, another x out here, another r. I've got r squared on the bottom, so I'll actually have r squared times r. X over r is the cosine of theta. R squared I had before, and I'm one step away. This will give me r cubed in the bottom. Well, this is r. R cubed will be x squared plus d squared to the 3/2. So this integral will turn into k lambda x dx over x squared plus d squared to the 3/2. And I think we may have done this integral not too long ago. But this is one where our limits for x are going to go from minus infinity, that's an 8, not an infinity, but close enough, to positive infinity. Okay, well, actually, did you learn about even and odd functions in calculus? Is that something that you study? Does that sound familiar to anybody from second quarter calculus?
Yeah.
Okay, this is an odd function. Okay, when x is negative, this function's going to be negative because of the x up here. When x is positive, it's going to be positive, and it's symmetric because if you put in a negative 50 meters, you'll get a particular negative value. If you put in positive 50 meters, you'll get the exact same value, but it's going to be positive. And I'm pretty sure that's what we call an odd function. Well, if you integrate an odd function over symmetric limits, like minus infinity to infinity, or minus 5 to 5, or it doesn't matter what they are, if they're the same values but opposite signs, this integral is going to be 0. And so you don't have to evaluate this. If you actually do evaluate it, you'll find out that it does come out to 0. So let's take on the y integral and find out what's going on with it. Now, here's something that's going to help us with that. The y integral is going to be the amount of the electric field that's pointing away from, or that part of the electric field pointing away from the thing. And if I sketched the electric field for the left half and the electric field for the right half, just briefly, and this is another symmetry argument, but it'll let me avoid some scary work on this thing. By the way, this calculation is going to be way simpler once we get to Gauss's law, and I'll show it to you at the end of today anyway. So there's our infinite line of charge. Here's the quote unquote center of it. So this is where our origin happens to be. But if I come out here a distance d away from this thing, I would expect the electric field from the entire left side of this thing to point in a direction that looks like this. And I'd have to actually do the integral from minus infinity to 0 to figure out what this thing is actually going to be. But that's I'll call that E sub L for the electric field from the left side. For that from the right side, I'd expect the electric field to point like this, and this will be E sub R, and this value will have the same magnitude as this value does, and will make the same angle with the horizontal because I've got symmetry. The charge on the left side is exactly the same as the charge on the right. I won't use theta, I'll use phi for this because we're using theta for something else. But there's my, what that will look like. Now, that means these two are going to have the same x and y components. So if I just calculate the y component for 1/2 of it and double it, I'll get the y component for the whole thing. So I'm going to do that, and it'll save me from horribly complicated stuff. Anyway, let's see. I'm going to let's see, sine of theta is going to be d divided by r. So d over r. dq is still lambda dx, and r is still the square root of d squared plus x squared. So what this whole thing turns into then is e sub y is going to equal the integral of k lambda dx. The sine theta is d divided by r, and I've got this r squared that was there in the first place. This is the only place that's going to show up, but e sub y will equal the integral of k lambda d dx divided by, this is r cubed, which is, so it's going to be x squared plus d squared to the 3/2. And for my limits of integration, I'm only going to go from 0 to infinity, but then I have to multiply by 2 because that's only half the rod. So let's figure out what the radial component of the electric field happens to be. And e sub y, integral of, let's see, if I pull all the constants out, I'll have 2k lambda d, and then the integral that I have to perform is actually 0 to infinity of dx divided by x squared plus d squared to the 3/2. Okay, that's on my integral list, which, oh, I had it out yesterday. Here it is. Oh, I've been messing around with so many things. Let's see. This is one very much like it. Let's see, what have I got? dx on top, x squared plus d squared to the 3/2. This is x squared plus a squared to the 3/2. I just need to replace the a in this expression with d, and I'll get 2k lambda d, and then times 1 over, not an a, but a d for us, d squared, and then d divided by the square root of x squared plus d squared. And whoops, not d, but x on top, excuse me. And I evaluate that at 0 and infinity. So let's see what this thing turns into. May have to do a little bit of work to simplify that, but the d over d squared, that's just going to give me 2k lambda over d. And this thing, I'm going to factor, let's see, if x is 0, if x is 0, I don't have much of a problem, I don't think. But I would have x divided by the square root of x squared plus d squared evaluated at infinity minus x divided by the square root of x squared plus d squared evaluated at 0. And I know this is probably completely unconventional notation, but if I evaluate this one at 0, no problem. Put a 0 on top of this thing and I'll have a d squared on the bottom, or the square root of d squared. That's going to be 0. But this one is not so obvious. I've got x divided by the square root of x squared plus d squared evaluated in infinity. It looks like I'd get infinities top and bottom, but I can pull a stunt with this thing. You could probably use L'Hopital's rule, I think, but which I don't remember exactly, except taking derivatives top and bottom as far as I remember. But I can also factor an x out of this radical down here, and it would turn into x over x times the square root of 1 plus d over x quantity squared. And these x's will divide out, leaving me a 1 on top. And if I evaluate that at infinity, this term vanishes at infinity because d divided by infinity is 0. And so I'll end up with 1 for this whole thing. So my e sub y ends up just equaling, I get a 1 here and a 0 here. It'll be 2k lambda divided by d. This is interesting. For an infinite line of charge, the electric field doesn't get weaker with the square of the distance, but just inversely with the distance. So that's kind of an interesting thing. I can write this differently. If I remember that k is 1 over 4 pi epsilon naught, then I'd get a 2 lambda on top, a 4 pi epsilon naught d on the bottom, and the 2 over 4 gives me a 1/2. So it's lambda over 2 pi epsilon naught d. So we just figured out the electric field a distance d away from that thing. You're going to appreciate Gauss's law when we get to it, because I can figure out, using Gauss's law, I can do this thing in probably less than 30 seconds, I think. And that's what I use for an infinite line of charge. I don't bother going through this integral, and you'll like that. So back to this problem. Now that we know what the electric field is, lambda over 2 pi epsilon naught d. So okay. Consider an imaginary cylinder, radius r equals 0.250 meters, length of that, and it has an infinite line of positive charge running along its axis, charge per unit length, blah, blah, blah. What's the electric flux through the cylinder due to this infinite line of charge? Okay, well, we already know that the electric field everywhere is radially away from this wire. Okay. Which means there will be no flux through the end caps, because the electric field will be parallel to the faces of those end caps. So all I have to worry about for the electric field is that it's going to be, let's see, or at least the flux is that it's going to be through the curved part of this. Well, if you imagine a little curved part of this thing with an area dA, and this would be my dA vector, which is going to equal the area of this thing in, we could call it the n hat direction if we want to. The electric field is going to point in the same direction. And so the little bit of flux that's through some area dA, the flux sub E, will equal E dot dA. The dA part is my dA in the n hat direction. The electric field part will be this thing, lambda over 2 pi epsilon naught d in the n hat direction, because it's pointing radially outward too, just like that n hat is. And n hat dot n hat is 1. So I would end up with the flux through some little chunk of the area is just going to be lambda over 2 pi epsilon naught d times dA, and no more vectors. So to figure out the total flux through it, I'll just integrate that expression. Okay, lambda over 2 pi epsilon naught d. This stuff is all constants times dA. Well, this looks familiar, except I'm not getting the surface area of a sphere this time, but I'll have lambda over 2 pi epsilon naught d times the integral of dA over the curved outer part of the cylinder. Remember, the end caps don't make a contribution. Well, let's see. What's the area of that going to be? It's going to be the circumference of this thing, which I can call 2 pi r if I want to, and r is 0.250 meters. So it'll be the circumference times 2 pi, that's where that is the circumference, 2 pi r, times the length. If you imagine slicing this thing down on one side and laying it flat, you'll get a rectangle that looks like that. So the flux of the electric field will be lambda, oh, I shouldn't call it R, I'll call it D. That's what letter I was using. Lambda over 2 pi epsilon naught D. And then the area of that curved part was 2 times pi times D. Let's see, times L. That's what I get. Well, there's some stuff that divides out here. The D's go away. That means it doesn't matter what the diameter of the thing happens to be. And the 2 pi's go away. And I end up with lambda L over epsilon naught Okay, lambda L, lambda is charge per unit length. L is the length of my cylinder. This is the charge that's enclosed by this imaginary cylinder that we've got. And the net flux through the surface ends up being the charge enclosed divided by epsilon naught, exactly like it did for the sphere. But this was a different geometry, but it still comes up being Q enclosed over epsilon naught. Well, that's neat. That's actually half of Gauss's law, is that the net flux through a surface will equal the charge enclosed by that surface divided by epsilon naught. Okay, what else we got going on here? What's the flux through the cylinder if its radius is increased to r equals 0.500 meters? We didn't actually calculate the flux on this, but if we doubled it, it wouldn't matter because the flux didn't depend on the radius of the cylinder. Okay, and then the flux through the cylinder if its length is increased to L equals 0.800 meters. All right, well, that would be doubling it. We'd have twice as much flux. So let's actually calculate what this will be. For the original problem, Q enclosed over epsilon naught, which is lambda L over epsilon naught, we have lambda was 6.00 times 10 to the minus 6th times 10 to the minus 6th coulombs per meter. The length L of it initially was 0.400 meters. And then epsilon naught is probably not something you have memorized yet. It is on oops, that's the wrong class. It's on the formula sheet. It's about 8.85 times 10 to the minus 12th. Okay, units here. It's going to be Coulomb squared. Let's see. I think it's meters squared per newtons. Although, let's see. Nope, I've got something backwards here. I think the meters squared has to come down here. Oh, I guess I could look in the textbook, huh? For units. Yeah, epsilon naught, 8.85 Coulomb squared per Newton meter squared. Newton meters squared. There we go. All right, well, what's that all come out to? Can't do that in my head. Hope I did this right. See if it makes sense. I'd get about 3/4 times 10 to the 6th times 0.4. Yeah, I get 2.7 times, I got 3 sig figs, 2.71 times 10 to the 5th. Now, unit-wise, let's see. I'll have Newton meters squared that come up top. These meters go away. So I'll have Newton meter squared per Coulomb. Is that what we had for units for electric flux the other day? Or not? Does that sound familiar?
Yeah.
Okay. Yeah, so that's what we have. And the last part says, what's the flux through a cylinder if its length is increased to that? Well, that's double the length. And it doesn't matter what the radius is. We found that out. So we'd have 5.42 times 10 to the 5th Newton meters squared per Coulomb for the second part. All right. That's enough with trying to solve Gauss's law problems or electric flux problems without Gauss's law. Let me now give you Gauss's law. And here's what it is. Through a closed surface, the net flux of the electric field is going to equal the integral over that closed surface, and that's how we denote an integral over a closed surface, of E dot n hat dA. And I can't remember if your book uses this notation or this notation. It may call it E dot dA, but I think your book uses the n hat dA. And that will equal the charge enclosed in that closed surface divided by epsilon naught. And so that's Gauss's law right there. And your book, I think, puts an apostrophe S for that. There are books that forget the apostrophe S and just use the apostrophe, so they call it Gauss law. But I grew up taking this class out of a book that called it Gauss's law, so I'm forever stuck using that. And I think your book does that. So there it is. Now, here's how you can use that. There are 3 situations of nice symmetry where you can actually use Gauss's law to figure out the electric field. And one of them is for this infinite line of charge. And you appeal to symmetry on these things every time you do it. But let's figure out that electric field. Pretend we hadn't done it today. Okay, so here's our infinite line of charge. And I will draw what we call a Gaussian surface. Those are the surfaces that you integrate over for Gauss's law to use it. And I'll just imagine that I have this infinite surface here, and it's got a length L and a radius R here. Looks like that. And from symmetry, I expect the electric field to point radially away from this infinitely long uniform charge density, because if you look down that charge density this way, it's the same in every direction. So whatever the electric field happens to be, it'll be like that. So I'm going to take a little chunk of this thing that I call dA in the n hat direction, and that's the direction that I expect the electric field to point. And so the E dot n hat dA part of this will become E in the n hat direction, whatever the magnitude of it is, some distance R away from the center of the wire. But I don't know that distance dependence yet. That's something I'm figuring out. E dot n hat dotted with n hat dA. And let's see. N hat dot n hat is 1. So this ends up being EdA. So that's what my integrand has become. And I would expect the electric field to be everywhere the same on this imaginary Gaussian surface with a radius of R, because I'm always the same distance away and the electric field should always point away. And so I can pull it outside of the integral. So my integral is going to become, let's see, EdA over this closed surface that I've got. Pull the E out because it's constant, and it'll be over this closed surface, the integral of dA. Now, there are parts of this surface that I've got where the E dot dA part's going to vanish at the end caps, because the electric field should point radially away, and on the end caps, that would be lying in the plane of those things, and the E dot n hat dA part is going to vanish. So I only integrate over the curved part. So I'll have E times, not a closed loop integral this time, but just EdA over the curved part. And so I just get the area of the curved part. Well, that was equal to its circumference times its length. And so that will end up being 2 times pi times r times its length. So there's that stuff. So E times 2 pi r L, it's going to equal the charge enclosed over epsilon naught. Well, how much charge is enclosed in this thing of length L? That's going to be lambda dL. I forgot to define lambda for this particular problem, but it'll equal lambda L over epsilon naught. And something that happens is the L's divide out, and I can get the electric field strength is going to equal, or just E by itself, if I divide by 2 pi RL, I'll get lambda L over 2 pi R L epsilon naught, and the L's go away, and I get that expression that I had, or something, I had a D in it before, but I get the electric field is just lambda divided by 2 pi epsilon naught r. Now, I talked through that a whole way. If I'm just calculating it and not explaining it to somebody at the same time, I can race through that a lot faster. But that's how you can use Gauss's law. There are only 3 situations where you can use Gauss's law to figure out the electric field, and one of them is something that we know already anyway. It's if you have a spherically symmetric charge distribution, then the electric field, you can calculate the electric field a distance r away from the center, but we already know that that happens to be kq over r squared, or 1 over 4 pi epsilon naught r squared, q over 4 pi epsilon naught r squared. So that one's not so interesting. The other one is an infinite plane of charge, and we'll do that one tomorrow, and then start looking at consequences of all this. So read about Gauss's law. Can't stress enough to read the sections of this chapter. It's kind of mind-boggling, but your understanding of it will improve with repetition. And so read it, check out the examples, try to reason through as many of those as you possibly can. Okay, any questions? Let's see. What's going on? Oh, I'll be posting a new homework here, and Noah, I can, let's see, anybody that wants to, later today, I'll be able to maybe meet and discuss the homework. Like, let's see, let's say after 2:30. I'll probably be eating lunch at 2:30, but after 2:30, if there's some time that would work out for people to discuss the homework, we could do that. So you could send me a message and I can set up a Zoom meeting. And what else? Oh, the lab for this week is going to be one on Gauss's law, and it's a worksheet kind of thing. And I'd like to maybe at least show you that thing tomorrow morning, and then you can try to work through that as much as you can, and we can bounce back and forth with questions on it over the next few days. And I'll give you a week on that to finish it up. So I'll post that soon. Oh, we have a chat here. There must have been a question that popped up. Oh, okay. That's what I saw before. All right. Well, let's stop for the day, and I'll see you tomorrow morning. Or some of you I'll see this afternoon if you want to have a meet for a Zoom meeting.